Aha, the dreaded sun and the solar radiation, etc. Okay, how are we going to do this? Okay, so show that the intensity of the solar radiation, right? The first thing you want to do is figure out the power output of the sun, right? Which in astrophysics we call the luminosity, which is just going to be E epsilon or sigma. Sorry, I think that's a sigma. Is that a sigma? Lowercase sigma a t to the fourth, right? Okay, so we've got the temperature. That's good, right? The area is going to be 4 pi r squared for the sun, and there's your r, right? And then for stars, we just say that they're perfect black bodies, that they're perfectly able to radiate. I don't know if that's actually true. And then look up sigma. Look up the Stefan Boltzmann constant. Okay. Is it the Stefan? I think it is. You know, having said that, I should make sure I'm not saying something that's just wrong. Yeah, it is. Stefan Boltzmann. All right. Okay, so that's the power. That's the first step. Find the power output of the sun. And this is going to be a big number. It's roughly 4 times 10 to the 26th. Okay. The second step is to figure out what the intensity is, right? And the intensity is power divided by area, right? Okay, because it's watts per square meter, right? Okay, so what we do is we take that power of the sun, and I'll call it power of the sun. The power of the sun. Okay, that's going to be, you're going to take the power of the sun, then divide that by 4 pi r squared. And this pi r squared is not the radius of the sun. It's the radius of a sphere whose it's the radius of a sphere whose radius is the orbital radius of the Earth, right? So this is how far we are from the sun, right? 1.5. Because remember, the sun is here, and all that nice, lovely, roughly 4 times 10 to the 26th watts is being spread out over this area of this sphere that is as big as our orbital radius, as big as the distance we are from the sun. Okay, so that's what we do. We say that the sun is radiating all of that wattage of power over this area evenly, right? That might not be totally true, but let's just go with it. Okay, so we divide by that. And this, by the way, is in the data packet in the astrophysics sections. Brightness is luminosity over 4 pi d squared, right? And the brightness is the watts per square meter. But anyway, I got something that was very, very close to 1400. Okay, it's like, anyway, I'll just say that. Okay, so then it says the albedo of the atmosphere is 0.3. Deduced that on the average, the intensity of the surface is 245, right? So remember that that roughly 1400 watts shines in on the surface, right? Okay, 30% is reflected. That's 30%, right? And 70% is absorbed. Okay, so you're going to take that number and you're going to multiply it by 0.7. And that is what makes it through the atmosphere, right? All right, now you've got this whole issue of the frontal area versus the surface area, right? Remember that the Earth, as seen from the sun, is absorbing over an area of pi r squared, okay? But it's actually rotating, right? So we're talking about the average spread out all over the whole Earth, right? And so you have to spread that out over 4 pi r squared. Now, this gets, by the way, it has to get more complicated as we get closer. Say the Earth was really, really close to the sun. It wouldn't actually illuminate a hemisphere, right? And so it would get more complicated. But we're just going to say it's the Earth is sufficiently far from the sun, and it is, that it essentially illuminates a hemisphere. And that's because the orbital radius is much, much bigger than the Earth's radius. Okay. So you're then going to multiply by pi r squared divided by 4 pi r squared, right? Because this intensity that you get, right, that shines on there, makes it through the atmosphere is absorbed on a pi r squared area, but it's spread out over a 4 pi r squared area. So, just divide by 4. All right. So estimate the average surface temperature of the Earth, right? Okay. So what we're going to do here is we're going to say, okay, the intensity, which is the answer to this, right? Okay. And I got something that rounded up just slightly to 245. So it's really very close, right? So whatever that intensity is, you're going to go the intensity of that times the surface area of the Earth, right, is going to equal E sigma, the surface area of the Earth, temperature to the 4th. Okay. Now, I mean, go ahead and put it would be 4 pi r squared, right? But the surface area of the Earth cancels, okay? The second thing is that they haven't given us the emissivity of the Earth. So they must want us to use 1, okay? So there it is, right? So whatever that intensity is, that 245, right, you're just going to say that equals Stefan Boltzmann constant T to the 4th, right? Solve for that. And you get something between 250 and 260 kelvins, just going to say, okay? That's what you get, okay? Then it says the average surface temperature of the Earth is actually 288, right? So you're getting something that's around close to somewhere between 250 and 260, right? But it's actually 288, right? Suggests how the greenhouse effect helps explain the difference between the temperature estimated in C and the actual temperature there. So I do want you to be sure, I mean, go do your best. We've talked about the greenhouse effect, et cetera, right? Remember that, I'll erase everything. I'm going to erase everything in 3, 2, 1. It's gone. Remember that here's the Earth. Here's its nice atmosphere. This is a gross exaggeration. The atmosphere is not nearly that big. The atmosphere is actually like a coat of varnish on a basketball. If the Earth were the size of a basketball, the atmosphere would be as thick as a coat of varnish. Now, of course, that's not very helpful because, how much thinner did you put in the varnish? I think just, thin anyway. Sub-millimeter, right? Anyway, okay, so the important thing here is that this atmosphere has these greenhouse gases, right? Remember that greenhouse gases can pass, like short wavelengths, can pass right through it. They can pass the short wavelengths, but they absorb long wavelengths. Remember that the sun is hot. The wavelength of the sun, right, it's going to be 2.90 times 10 to the minus third over the temperature, right? This is a big number for the sun, like 5,800 kelvins, right? Okay. So for the average, sort of like the peak wavelength is somewhere right in the middle of the spectrum. It's a nice yellowy green or something like that. Okay. So that's a very short wavelength, but when the Earth is radiating, it's radiating at 288 kelvins, right? So that's a much longer wavelength. So the light can get in, the energy can get in, but when it tries to go out, the atmosphere absorbs those longer wavelengths. Absorbs the longer wavelengths, okay? And it re-radiates it, not always back to the Earth. It doesn't sound like a mirror. Okay, it radiates in all directions, but some of it goes back to the Earth. It warms the atmosphere. Yeah. So it's a bit more sophisticated than people say. It's just like, well, it acts like a blanket. Can you be more specific? Anyway. Sorry about that. That was a rant.